your lesson on 1.3 is actually a partial review of some topics. Some of them are going to be very familiar, and you're going to be happy to see them back, like end behavior. And some of them are brand new, and your very brief introduction to calculus, like limits, and then also continuity. So I'm going to show you a little bit about what calculus components would be for this lesson. But then I'm going to be very honest and frank with you and tell you what I expect from you at pre-calc level, because it's called pre-calc for a reason. You're not doing calculus yet. So this is, I don't think, on your worksheet anywhere. If it is, or maybe it is. Is this on your worksheet? Oh, good. It's right at the top. So it's talking about whether a function is continuous or not. And there's technically 3 things that have to be satisfied to determine if something is continuous. Now these 3 things, this checklist, this is really a calculus question. So the first one says, f of x is defined at c. In other words, f of c exists. So the way I read that as, like, what does that mean? Because that's, even though they tried to simplify it, it still sounds really confusing. I just say, there is a point. Sounds very deep, doesn't it? There is a point. So if I ask you to determine if a function is continuous at x equals 2, your first job is to make sure that there's even a point at x equals 2, because maybe there isn't. Then, whoops, once we determine that there is a point, then you're going to do what is really a calculus concept, but something you guys can understand when we look at a table. We're going to figure out if the function approaches the same value from the left side and the right side. So what that means is that the limit exists. So then you guys are like, great, what's a limit? Y'all seen Mean Girls now, right? So I love that movie. The limit does not exist. Yes, it's that thing. That thing is a limit. So that still doesn't tell you anything, does it? So in calculus, a limit is what the function is approaching as your x approaches a certain value. And we've seen functions that do some crazy things, like go off to infinity, you know? So we're basically asking ourselves, if I look at from the left side and the right side, are we approaching the same output value? Whatever that is, okay? And then the third thing in the list is basically that the point and the limit are saying the same thing. So that the point, the y value of the point specifically, matches the limit. So if I plug in x equals 2 and I get a 7, and then I look at the limit from both sides and I get a 7. 7 matches 7, therefore the function is continuous at x equals 2. That's what you would have to do in calculus. And that's a super fun time, and we'll save that for next year. In our class, what I'm going to ask you to do on the assessments is just determine whether something is continuous, either by looking at the picture of the graph or looking at a very specific point. So this is just kind of a fun warm-up question for us, because I know what's coming up in our lives here. So let's warm up with this one. This is not on your paper anywhere, but I have this really funky piecewise function. My first question to you is, can you tell that that is not continuous? Yeah, there's a gigantic gap right here. That can't be good. That's called a discontinuity. It's specifically called a jump discontinuity. You guys are not going to be forced to memorize the type of discontinuities. You didn't have a chair. Sorry. But, you know, it's fun if you know it. And then right here, there is a hole. That's called a hole. That's interesting. So let's talk about how we evaluate this function. F of 2. Well, since I don't actually give you the algebra part of the function, this piecewise function, you are going to have to just look at the graph. So I go to where x equals -2, which this graph counts by 2, so be careful. And then I go find the function. So I have to travel down to here. And then there's an ordered pair right here. Can you tell me what the output is? Can you guys see? I know you're in the back. It's hard to see. -2 is also the output. So then it says evaluate this function at -6. So I go over to -6, and then I go find the function. And then I look down here and I see this, which is an open circle. So what's the point at an open circle? There is no point. So what is the output? We actually had one on our homework kind of like this. It is undefined at -6. There is no point. So remember that 1, 2, 3 list? Number 1 would have just had a problem. Not continuous. All right. And then f of 0. So I go to, I look up. I look down. I don't see any points. So it is not defined. It is undefined at 0. Now these questions are backwards. This time I'm going to give you the output. So I'm telling you the y value. I want you to go figure out what the input was. So if you get an output of y, so 2, I look up here at y equals 2, and I go find my function. Boom, right there. Can you tell what x value gave you an output of 2? 6, very good. And then this one's always a hoot. Y equals -6 would be down here. Uh-oh. I look left. I look right. I don't know. Which one's the right answer? They're both the answer, yeah. And unfortunately, they're not even, like, on the corners they're not on the edges of the boxes, so I don't really know what this number is, but I'm just going to make something up and say it's approximately -5, even though it's not. And then I don't really know how far over this guy is, but I'm going to make something up. I'm going to say it's like 7.2. I don't know. I totally made that up. So in this case, guys, because I didn't give you an algebraic function, you couldn't possibly tell me with certainty what the outputs or inputs were in that case. So I would have to take a little bit of error in your answers. Like you might think it's 7.2 and you might think it's 7.0, and I don't care. So anyways, if it's on a test, I can almost guarantee you that I give you the algebra function because I don't like to grade things where there's uncertainty. That's annoying to grade. These are some more graph questions that we can look at for review. Instead, I'm going to show you this picture. This is from your textbook. And it goes through the definition of being a continuous function, and then it starts to introduce you to the concept of a limit. So this is the point C right here. This ordered pair C comma f of C. And when they ask you about whether the point exists, that is just asking, is there a point there? Now I can't really see this, but I think in your textbook it's actually a hole. So there actually is not continuity in this graph because of the hole, but there is a way to evaluate what you call a limit. So even though I can't plug in C to the function for some reason, because it has what's called a removable discontinuity, we'll talk more about that later, I could figure out the y values as you get really close to C on both ends. That's what a limit looks like. So if this was the number x equals 3, maybe I can't plug in a 3, but what I can do is plug in like a 2.99999, and I can plug in a 3.00001, and I can figure out what y value it's trying to approach. We are going to totally talk about limits like in April. So we're going to put a little pin in the limit concept for a question for the time being. What we are going to talk about is discontinuity. So you need to be able to look at a function and determine if it's continuous or not. Unfortunately, sometimes the discontinuities are hard to see. This one's not. Anyone know what this is called? Asymptote. Very good. Points for maturity. Did you giggle at that in Algebra 2? No. That's my maturity test for my Algebra 2 kids. When I say asymptote, whoever giggles, I kick out. No. So this is called, technically it's called an infinite discontinuity if you want to give it a name, but you are right. This is a vertical asymptote. There also happens to be a horizontal asymptote. This is a rational function. We are going to do tons of rational functions in a couple months. So we'll come back to those concepts, but I can see that there's a discontinuity for sure. This is maybe like an example of a piecewise function, and this particular one, when it was graphed, has a very large gap. This is called a jump discontinuity. And then there's a cute little one called a hole. For you guys, it's called a hole, but in the discontinuity chapter, they call it a removable discontinuity. We'll talk about why that name and what it means later when we do the rational functions chapter, but the idea is you can algebraically remove it from the equation, therefore saying there is a hole, but I can still graph the rest of the function. So that's fun. All right, we'll come back to that. Let's look at this example that is already done in your notes. They gave you a function, 2 times the absolute value of x plus 3. And what they're going to do is this is what you would have to do in a calculus course. They would have to prove continuity by going through that 1, 2, 3 step process. So the first thing they want to know is it continuous at x equals 2? So they said, I don't know, let's start by plugging in x equals 2. So when they did 2 times the absolute value of 2 plus 3, they get 7. So since there is a point, that thing is satisfied. Check. The next thing they're going to do is they're going to look at their table. So they're going to put it in ask mode. They're going to type the function in y1, and they're going to look at points that are to the left of 2 and points that are to the right of 2. Now look at your y values as you get closer and closer to 2. What's happening to your y values on both the left and the right hand side? They're getting really close to what number? 7 here and also 7 here. They're just approaching 7 from the opposite side, so top and bottom. So this guy says the limit as x approaches 2 is 7. And it's on both sides. So the limit exists, the point exists. Do the point and the limit match? Did they both give you the same output? Yes, they did. So since they match, this is continuous at x equals 2. That was a hoot. Let's never do that again. We're not going to test you on that because limits are not part of our vocab really yet in PreCalc. But can we look at this example? It's already done on your paper, so you don't have to do any work. This is called a rational function. Any function that has x, a variable located in the denominator, is considered a rational function. And these are the ones that produce those weird asymptotes, the vertical and horizontal asymptotes. So I want to know if it's continuous at x equals 1. And this is the kind of thing I'm going to ask you. I'm not going to make you go through this, but I am going to ask you to tell me if it's continuous at one particular value. So go ahead and plug in x equals 1. So you get 2 times 1, so 2, over 1 squared minus 1. Oh boy, what's going to happen? You're going to end up with 2 divided by 0, which we know in math is undefined. You cannot take two things and divide them into 0 groups. That's called magic, not math. I know they're close. So the point doesn't exist. So if my question to you was, is it continuous at x equals 1? Your big answer would be no. Now, for funsies, they said, let's continue on with the checklist. Why not? Because now in calculus, not only will they want to know why it's discontinuous, and then they want you in calculus to determine which type of discontinuity you have. So remember our options were like that infinite discontinuity, a jump discontinuity, and a hole. Again, this is a calculus skill, so we're just going to show you because it's fun, and then we're going to forget it until April. So what they did was they went to their table, they typed in their function, and they looked at the left side of one, and then they looked at the right side of one. So what's happening to your y values when you look at the left side? What's going on there? Are they? Because this says negative 999. The next one's going to be negative 9999. The next one's going to be negative 999999. What's happening? They're getting super uber duper negative, largely negative. What are they going towards? Negative infinity. Aren't they approaching negative infinity? Like they're gonna just keep going, like forever. So you guys are looking at me like, what is she pointing at? So then look at the right side here, guys. What's happening to your y values as you look on the right side of one? They're getting bigger and bigger and bigger, but instead of going down to negative infinity, they're going to positive infinity. So on the left side, the function was traveling down forever. On the right side, it was traveling up forever. We would have one of those beautiful vertical asymptotes that you guys love to see. Not. Okay, so clearly not continuous, and if a calculus student was asked what type of discontinuity, this is called an infinite discontinuity. Oh, that's a piecewise function. So, piecewise functions sometimes are continuous. There are moments in piecewise functions where the two endpoints match up. You had that a little bit in Algebra 2, where like you had an open circle up here, but then you went to go plot the other side of the piecewise function, and it closed it up because it overlapped. So just because it's piecewise doesn't mean it's not continuous, so be careful. This one's not continuous, though. They want to know if it's continuous at x equals 2. So what you're going to have to do is approach 2 from both pieces of the function, even though you're not supposed to. For this type of question, you get to use both functions. So normally, if I was plugging in x equals 2, I would only use the bottom function. So when you plug in x equals 2, you get 2 minus 1, which is 1. But I'm curious what's going on the other piece, even though it doesn't exist. I would have put an open circle at this point that I'm about to find. So if I was to plug in x equals 2, 2 times 2 plus 1 would be a 5. So think about this, guys. On your piecewise function, when you're graphing this, you would have a normal point at 2, 1, and then you would have plotted an open circle at 2, 5. And, you know, if you're curious, this function would have looked something like this. We'll talk more about graphing piecewise functions in the near future. Does that look continuous to you? No? Anyone want to take a stab at what kind of discontinuity that was? It's a jump. Very good. All right, this guy. I don't even think I need to do all this work, guys. What is this? X squared plus whatever. What kind of a graph is this? It's a parabola. A parabola is continuous everywhere, guys, because what's the domain of a parabola? Negative infinity to infinity. So I don't really have to overthink this one, guys. Just plug in a 4. So if you plug in a 4, 16 plus 20, 30, 39. So the answer to this question is yes, it's continuous. That's all they wanted to know. Now, technically, we were supposed to prove it. We were supposed to get our table out, and we were supposed to plug in like 3.999 and 4.0001. But take a wild guess what would have happened. We would have got numbers that were really, really close to 39. So I'm going to skip that. So, by the way, anytime you get a polynomial, they're continuous. You don't have to do any work. And if you need justification, you can just say, it's a polynomial. They're always continuous. However, these guys aren't. So flip to the back of the worksheet temporarily and look at number 6. This looks a lot like the question I'm going to give you on your test on Friday. I give you this, which is not a polynomial because you have x in the denominator. This is called a rational function. And rational functions are often discontinuous, but not always. And they're not discontinuous at every value. So I'm going to ask you, is it continuous at x equals negative 4? The only thing that would make a rational function discontinuous for us in PreCalc today is if the denominator came out to 0. So write yourself a big note that the denominator cannot come out to 0. So let's look at that, guys. If you take negative 4 and you plug it into the denominator, you get negative 4 plus 4 in the denominator. What did I just say about denominators, y'all? It can't be 0. So my question is, are you continuous at x equals negative 4? And the answer is a big fat no. I don't think I have to do any work on this one. The question says, is it continuous at x equals 1? Yes, tell me why. It's a polynomial and they're always continuous, so we're done. Yes. All right, so we're still on that worksheet. We have another rational function. Here we go. But this time, and this is what your test looks like, I'm going to have you determine if it's continuous at a couple different numbers. So let's start with x equals negative 1. So all you need to do, guys, is look at the denominator. When you plug in a negative 1, you get negative 1 squared plus 3 times negative 1 plus 2. I think that's 0, y'all. Isn't that 0? So is it continuous at x equals negative 1? No, it is not. All right, well, then let's go ahead and try x equals negative 2. So negative 2 squared plus 3 times negative 2 plus 2. I think that's 0 again. 4, yeah. Right? Is it? Yeah. So no. Yeah, what'd I mess up? Yeah. Right. So that's good segue. What we have here is called a removable discontinuity. So it's still a discontinuity. Great question. And what's going to happen when we learn about rational functions again is you guys would have actually factored this, and it would have factored into x plus 2 times x plus 1. So when your Algebra 2 teacher and PreCalc teachers ask you to graph this now, you're going to notice that x plus 1, the factors literally cancel from the problem. But that doesn't mean they never existed in the first place. So there's still a discontinuity, but these are called, this is what a hole looks like. Whoa. Deep. Good question. Excellent question. So we're going to recover all this rational function stuff later, but it's still a discontinuity. It's a different type. So if it was a calc class, or maybe a late pre-calc class, we would say, okay, what kind of discontinuity are they? So this one is removable. It's a hole. And this one is going to be one of those infinite discontinuities. That's an asymptote. Great question. All right. This is fun. When you get to calculus, you're going to talk about what's called the intermediate value theorem. And the intermediate value theorem states that, and this is actually what your calculators do when you're finding an x-intercept. So I'm not sure if this is on your notes. So if it is, it's probably on the front. The idea is if you have a function evaluated at a point where it gives you a negative answer, and then you go and evaluate it somewhere else and it gives you a positive answer. At some point in between those numbers, it had to cross the x-axis. It's a very profound theorem, isn't it? So if like I get -2 on this one, and I get 7 on this one, at some point it had to go through all of those other points, including 0. Because a continuous function wouldn't do anything else. It doesn't hop or anything. I know. Why'd they have to make a theorem for that? I don't know. Because someone got really famous for this theorem. Bob's theorem. I don't know. It's probably got a name. There's also a corollary called the location principle. So when you guys use your calculator to find the x-intercept, remember how you do second trace and then you pull up number 2, the zero finder? And your calculator asks you to give a left bound and a right bound point. It's using this theorem. So you have to give it a point to the left, which is sometimes above the function, sometimes below, depending on what it looks like, and then a point to the right, and it uses the intermediate value theorem to determine the intercept. Thanks, calculus. It's awesome. All right, we're not going to make you do those theorems, guys, so you can just etch-a-sketch the last 25 seconds from your brain. How's that sound? End behavior, that's familiar. You guys all know and love end behavior. Now, did you know end behavior is actually a limit and a calculus concept? But we're going to keep doing the simplified version of end behavior. But what I would like you to do, this is from the old textbook. We are not going to write end behavior like this. You guys are going to all get familiar with writing end behavior like this. F of x approaches something as x approaches -infinity. You can write this down at the bottom of the front of the notes. There's a little space there. F of x approaches something as x approaches positive infinity. Now, that's great. And I think for most Algebra 2 teachers, this is the exact template they use for end behavior. Cool. So that'll be an easy transition for you guys to PreCalc. Technically, we can reverse the end behavior, but this is the direction that your calculus teacher wants you to learn, so that's why PreCalc is doing it the same way. I need someone to translate this to me, though, because this is a lot of fancy math talk for one day. What is this saying right here? X, and this arrow means approaches. So as x approaches -infinity. What does that mean? As it goes to the left. That's literally what it means. As you look to the left. The question is, as you look to the left, what's your function doing? It could be doing a lot of things. And then what does as x approaches positive infinity mean? Translate that for me. As you look to the right. So we're going to learn later that these end behavior equations are something else technically. We're going to talk about that in the rational functions chapter. But that is the shorthand notation for end behavior. I remember all my Algebra 2 kids complaining about this because we told them they had to memorize it. And they're like, it's too long. That is the shorthand version of it. The actual end behavior answer is a paragraph of math. Would you rather write a paragraph of math? No? Okay, then we'll do this. So that is the template you guys have to use and memorize in that order preferably, because that way I know how to grade them easily. And I always do this order because my dyslexia would be a problem if I start flipping orders on myself. Okay. So on your end behavior questions, we're going to scribble this one out because I don't like that. And we're going to write our template. So you either need to be provided a sketch or provided a function that you could sketch, whether it's through your brain, oops, this is supposed to be negative, or through a calculator. But a minute ago, Matt told me that this was left. So I look on the left side. Where's my function going if you look on the left side? It's going down, 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 down to -infinity. And then he also told me that this meant right. So when I look on the right side of my function, it's going up, 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 up to infinity. So if you remember in Algebra 2 land, these answers were often negative or positive infinity, some combination of those two. But that's not always the case, so don't get happy with your infinities. All right, number 3, template that we need to learn and write down. Write it down. All right. I always joke that I want like a stamp with that. I could just stamp and behavior. That'd be great. birthday gift. Late birthday gift for me, huh? And behavior scan. All right. Left side. What's happening on the left side of your function? I don't know. Let's go look. Over here's the left side. Where's it going? Down forever to negative infinity. And then on the right side, what's going on? Going down as well. So this is a case where your end behaviors, both left and right end behaviors, were both approaching negative infinity, and that happens. Did you ever put this together in algebra? What type of functions produce end behaviors that go in the same direction, whether it's up, up, or down, down? Well, that guy, apparently. Parabolas would do that too, right? So what does a parabola and a quartic have in common? What's the degree on those? Even degreed polynomials, yeah. So when you have an even degree polynomial, your ends are either both going to go up or both going to go down. And some teachers like show you this beautiful chart of like, if you have even degree and odd, or even degree and a positive coefficient, then your end behavior does this. And if you have odd, okay, like there's no chance of me memorizing a chart for end behavior. So for me, I just visualize or graph the function and then do end behavior. So if you want a chart, guys, I'm sure there's one in this book, because this book has lots of charts. All right, this problem here, this is already graphed for you, but if it wasn't graphed for you and you weren't familiar with what a rational function did, which many of you are not right now, you would have to graph it. Now, can you guys do me a favor, just so we practice this for the future? When you graph this function, your calculator reads things horizontally, so you would have to put your rational function's numerator and denominator in parentheses. So just kind of make a note of self, because I think in your textbook for some of the questions, they just give you the function with no graph, and you're expected to graph it on your calculator. So if you type it wrong, you're going to see some gibberish. So make sure you use parentheses. But spoiler alert, this is what it looks like. So you can either trace along the left side, or later on we're going to learn some rules for end behavior, because it's actually approaching what we're going to call the horizontal asymptote in a minute. But could you all do me a favor? Could you get this typed into Y1 and then set your table into ask mode? Got a little close to that. Let's try that again. So besides knowing that this side means left, what we also have to think about is numerical inputs. So numbers that, for x, that are approaching negative infinity. So like, give me a number that's heading in that direction. Go pretty far. Negative 900. All right, go ahead and type in negative 900 and hit enter and tell me what output it gives you. Okay, something, something. Okay, blah, 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 blah. What? Oh, did you do more than negative 900? Okay, we'll get there. We'll go even more negative. Go like negative 9999999. Just start typing nines. Just make sure it's negative. 9. Okay, we're definitely approaching negative infinity though, right? Go us. And your calculator probably gives up on life and just calls it a 5. Yeah. Okay. Now, technically what's happening, guys, is it's not actually a 5. Your calculator literally is just going like, I don't care anymore. Like, it's close enough to 5. It only has so many character spaces, so at some point it's going to say, let's call it a 5. Because what's happening is your function is approaching the horizontal asymptote at 5. Not actually getting there. So now go on the other side of end behavior, which would be you plugging in gigantically large positive numbers. So like when you typed in a 900 or then went crazy and just put a bunch of positive 9s, you guys getting like 4.9 something and then like eventually it just gives up and says it's a 5. So this is how you could determine end behavior through your table if you weren't sure what was happening. So question for you. On the left side, as your x's went super duper negative, what was happening to your y values, your function? It was approaching 5. Now, did you notice it was approaching 5 from the bottom? It was approaching it from the 4 point something direction. What's happening over here on the right side? Oh, it's not 4.9, isn't it? Like 5.001? Yeah, sorry about that. Okay, so here it's still approaching 5, but it's approaching 5 from the top. And I can see that very clearly once I go look at my graph. So if you want to get extra fancy, you don't have to do this, by the way, but some college teachers really like when you put a little negative sign on that 5 and a little plus sign on that 5, because you're indicating which side of 5 it's approaching from. Isn't that cute? I won't make you do that, though. I'm skipping that, guys, because pretty sure we know what's happening on the end behavior there. Up, right? Up, and away. All right. This question's kind of silly. It says, here's a cubic function, and I want you to find any zeros that are located within this domain. So between x equals 6 and x equals negative 6 and x equals 2. So go ahead and type this into y1, but then for your window, I want you to change your x's to only show negative 6 to 2. For your y's, since I'm finding zeros, you don't have to really go anything crazy. You guys can just go like negative 5 to 5. And I haven't graphed this, but can someone tell me how many zeros you're seeing between that domain? How many times is it touching the x-axis? All 3 of them are right there? That's a bummer. You gotta find them all. Alright. So, determine between which consecutive integers the real zeros is. Okay, you should do this anyways. You guys should be able to look at your calculator and you should be able to estimate where the 0 is. So like that furthest one to the left, can you guys give me like a between two values thing that you're talking about? Is it between -4 and -5? Okay. So when you do the left, oh, you're getting weird looks. Do we not agree with that? Is it -3, -4? Yeah. I don't know. I don't have bifocals on. I can't be able to. So then it's between -4 and -5. That sounds right. Okay. So when you guys are doing the left bound, right bound stuff, when it says left bound, you need to give it something smaller than that. So you got to go -5. And then, so remember how I do the jumping thing on my calculator? Y'all can start doing that because you are technically using the intermediate value theorem. Yay. So then when it says right bound, I would say -4, and then boom, it's going to pop out that wonderful answer that she just gave you. All right. So I don't know about you. I'm super lazy. Some of you guys are also super lazy. So start to appreciate things in math that make your life easier. Like jumping instead of scrolling on your calculator. It's awesome. Use a little bit of brain power and you have like half the work. All right. Your homework assignment for this, we're going to skip these guys. It's on the blue sheet. And it's on page, that's not the blue sheet. Yeah. It's the 1.3 bookwork. It's on page 30 and 31. And it's numbers 3 and 9, 17 and 21. Now, I think in your instructions it says to do something different with 17 and 21. It says something like zeros to the 100th or something. So read that blue sheet. 23 and 27 and 31 and 37. So this whole assignment won't be due until the next homework check. So I can totally understand if you guys want to delay continuing on this assignment. However, I think we all learned the lesson the hard way. If you wait 7 days to complete a homework assignment from a lesson 7 days ago, you might be a little fuzzy. So maybe don't wait that long. But I can understand if you want to put it off until you finish getting ready for the summative on Friday. However, I suggest everybody does number 3 and 9. Because on your test on Friday, there's a question just like number 3 and 9. Okay. All right, lesson out.